Hi, this video will discuss temperature and the Arrhenius equation with regards to rates. So the rates of reactions are affected both by the concentration and the temperature of the reaction. And the collision model will account for both of these factors. Now, in general, if you are looking to increase the rate of a reaction, it increases with increasing temperature and increasing concentration of your reactants. If the temperature is higher, you're going to have more collisions taking place between the different reactants. And if your concentration is higher, you're going to have more of the collisions. So increasing temperature will lead to more collisions. Increasing concentration leads to more collisions. However, there's more that affects the rate than just increasing the reactant concentration and the temperature. You also have to have the correct orientation of the molecules when they hit each other. And here is an example of that. If I have a reaction between chloride and NaCl, so I'm going to draw it out here. We've got our chlorine atom, and then we have NaCl. So we've got the nitrogen will be in blue here. I'll put the oxygen in red, and then the chlorine in green. Right, the overall equation of this is we have Cl plus NaCl gives Cl2 plus NO. If these two were to collide in this orientation, you would have no reaction, because the chlorine needs to hit the other chlorine to form the Cl2. But if the chlorine strikes the nitrogen, or if the chlorine strikes the oxygen, you will not have that reaction take place. Only if you get the chlorine to hit with the other chlorine will this reaction occur. So if I have chlorine to chlorine, then you will have your reaction. So that's something that needs to be considered with the rates as well. How frequent are these ideal collisions that will lead to the reaction, and how often do we have these non-ideal collisions? And sometimes you could have molecules that collide 1 times 10 to the 10th times per second, but only every 1 times 10 to the 11th collisions is actually ideal and will allow for that reaction to take place. Something else that needs to be considered with rates is the activation energy, abbreviated as followed. Right, the activation energy is the minimum energy required to initiate a chemical reaction. Right, so minimum energy required to initiate your reaction. So the graph I'm going to put below does a good job of visualizing this. So we've got energy on this axis and time over here. any reaction that's going to proceed, the products have a lower energy than the reactants do. That's what makes the reaction happen, right? If you're going from a lower to a higher energy, that's not going to work, because the whole goal of that reaction is that it goes from higher to lower energy. That's why it happens. It won't happen if you go from a lower to a higher energy. However, in the process of going from a higher to a lower energy, you need to input that energy, and that is the activation energy. So if I start at this level, I have to input some energy, and then I'll come back down to an energy over here. So this is the reactants, and this is the products. The energy right here, that is the energy between the reactants and up top what is called the transition state, which is the highest energy point. This yellow arrow represents the activation energy. And that's going to be the energy required to initiate this reaction. Once we've gotten this input of energy, we drop down to much lower energy with the products. So oftentimes, the rate of the reaction is going to be determined based on how much energy needs to be input here. Now, using a catalyst, we are able to lower this activation energy. So now we only need that much energy for it to take place. So the reaction occurs much quicker. So this is with a catalyst. That is how the catalysts will speed up a chemical reaction, by lowering that activation energy. Now, how can we relate all of these different variables together? We do that through the Arrhenius equation. So the Arrhenius equation is as follows. K is equal to A times E to the negative EA over RT. So K being the rate constant, right? So I'll define all the terms. K is the rate constant. A is equal to the frequency factor. Now the frequency factor does not change really with temperature. It's going to remain pretty constant. And the frequency factor is related to the frequency of collisions and the probability that those collisions are oriented in a favorable manner. So I'll repeat that again. The frequency factor is related to frequency of collisions and probability that the collisions are oriented favorably, right? So the frequency factor will be different depending on what your reactants are. Now, EA is the activation energy. R is the constant, 8.314 joules per mole Kelvin. And then T is your temperature, specifically in units of Kelvin. Right, so based on this equation, the higher your activation energy, that will lead to a lower rate constant, right? If you plugged in the activation energy, you'll get a lower rate constant. If you have a high temperature, though, that will give you a higher rate constant. And you can check these out by going through and plugging in for each of these different variables while holding the other ones constant. So you can keep, activation energy constant and put in two values of T to determine how the temperature is affecting the rate of that reaction. You can do the same thing with activation energy and hold the temperature constant, right? I know this equation can look a little confusing in this form. So if you want to, you can take the natural log of both sides to eliminate this exponent. And doing that may make it a little easier to see. So if I take the natural log of both sides, I'll get ln of k is equal to ln of a plus negative EA over RT. Right, these are multiplied together, so when you take the natural log, you add those two together. So that is a way you can take it away from the exponent and bring it into form without that exponent.